Okay, so this video is about the definition of injective functions, some visual examples of functions which are injective and not injective, and then a brief proof that a particular function is injective. Hopefully, the proof at the end will help you guys when you're thinking about how to prove a function's injective on your upcoming midterm. So let's remember, if f is a function from a to b, we say f is injective or one-to-one if for all a1 and a2 in A, we have f of a1 equals f of a2 implies that a1 equals a2. Now, alternatively, we can take the contrapositive of this expression here to get the characterization if for all a1 and a2 in A, a1 is not equal to a2 implies that f of a1 is not equal to f of a2. So the characterization you pick might depend on the particular problem at hand. Sometimes you may find the first one easier to use and approve, sometimes the second one may be easier. It's sort of at your discretion to pick which one you want to use. Let's briefly look at a visual example of functions between two simple sets, so the set containing a, b, and c to the set containing d, e, f, and g, to see what visually sort of an injective function would look like. So if I say that f is going to send a to d, b to f, and c to g, and let's actually not call this function f because I have f as an element. Let's call it psi. Well, if you pick two different letters, then psi is going to output two different letters. So this psi is injective. Okay. Now, on the other hand, if I say that xi is going to send a to d, b to g, and c to g, well, then we have that b is not equal to c, and xi of b equals xi of c. Note that this is the negation of this particular implication here, right? P implies q, the negation is p and not q. So the not q is f of a1 equals f of a2. Whether a function is injective or not is less about what the function itself is and more about the domain and the codomain, in particular the domain. So let's think about the function f goes from some general set a to r by f of x equals sine x. Why don't we go ahead and draw just the graph of this function that we all know. So we know that sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of negative pi over 2 is negative 1, and sine of negative pi is 0 again. And then we're just going to draw the function by like connecting these dots. Not the prettiest, but it'll do the trick. Okay. I'm just going to copy this graph so that we can analyze the function on different domains. Let's first think about the function going from 0 through pi over 2 to the set of real numbers. So notice that on this particular interval, sine of x is strictly increasing. So if I give you x not equal to y, where x and y are in the interval 0 through pi over 2, so then x is less than y, or y is less than x. And so sine of x is less than sine of y, or sine of y is less than sine of x, right? And what this means is that if I give you different inputs, they're going to get mapped to different values. So sine of x is injective in this case. Okay, what about if we define the domain of our function, sine of x, to be negative pi over 2 through pi over 2. Oops. So here we have something similar. The function is still increasing along the entire interval. So if I give you different values in the domain, we'll get different values in the codomain. And the proof would be sort of exactly the same. Now, lastly, what about if we define the domain to be the numbers 0 through pi? Well, in this case, it's pretty easy to see that we can find different domain values that will map to the same output value, right? So let's call this x and y. Well, clearly x is not equal to y, but sine of x is equal to sine of y, right? So here, if we translate that into some sort of logical expression, we have x not equal to y and f of x equals f of y. But this is just the negation of x equals y implies f of x. X is not equal to y implies f of x is not equal to f of y, right? So when the negation of this statement is true, it means that the function cannot be injective. Let's consider a simple problem involving proving that a particular function is injective. So some of you will have seen this on a quiz, some of you will have seen it on a worksheet, and maybe others will have seen a very similar problem involving surjective functions, which I'll also cover. But I think it's a good example for, one, like just understanding good form when writing proofs, and two, recognizing like a strong strategy for getting started when you're asked to prove something. So how I like to start is, what are the relevant definitions in the statement you're trying to prove? Well, we're given that we have two injective functions, and we're trying to prove that some other function is injective. So the only thing we really need to know to solve this is the definition of an injective function. If we don't know that definition, then we won't be able to solve this problem. So why don't we start by refreshing ourselves on what it means for a function to be injective. So recall that a general function psi from x to y is injective if and only if we have that for all x1 and x2 in x, psi of x1 equals psi of x2 implies that x1 equals x2. So for this particular problem, this is the characterization of injectivity that's easier to work with. So after you've written all the relevant definitions, you begin the proof. Okay, you should always begin a proof by rewriting what you're given by the problem. In this case, that f from a to b and g from b to c are both injective. So we say, suppose f from a to b and g from b to c are injective. After you've restated your assumptions, you should write what you're trying to show. And that is that g composed with f, which is a function from a to c, is injective. So we want to show, I'll abbreviate that g composed with f from a to c is injective. Okay, so the reason I like beginning, before even starting the proof, I like to rewrite the important definitions is because you need to translate sort of what you want to show into sort of a more mathematical form by applying the definition that you know. So in this case, to show that g composed with f is injective, we need to pick arbitrary elements of the domain and suppose that g composed with f applied to those two elements is equal. And we need to conclude that the two elements are the same. So what do I mean by this? Well, the domain is A. So we're going to suppose that A1 and A2 are in A such that G composed with F of A1 equals G composed with F of A2. So now we're sort of stuck. But remember that we have our assumptions that tell us about nice properties of G and F. So most importantly, we know that G, which goes from B to C, is an injective function. So we can say, since G is injective, we know that G of F of A1 equals G of F of A2 implies that F of A1 equals F of A2. Well, that's convenient because we also know that F is injective. So that means that A1 must be equal to A2. And we're done. We've chosen arbitrary elements of the domain. Suppose that G composed with F applied to those elements gives you the same value. And we find, using the properties of G and F, that those elements must be the same. So we conclude by saying, therefore, G composed with F is injective. So this is a pretty simple example. There will be more examples coming in future videos, but given that a lot of you will have seen this problem, I think it's a good place to start. If you have any questions, please let me know.